All right, welcome to the sort of virtual lecture here. Let me get pointer set up and we'll get started. All right, so this lecture is mostly on cycloalkanes. We've introduced the naming of them, but we're going to talk about mostly chair conformations of cyclohexanes. So recall a couple things. Torsional strain is electron-electron repulsion. Electron pairs repulse one another. Steric strain is atom or group of atoms repulsion. These strains cause an increase in energy. Okay, we introduced those two terms. Now there's a third term now, is angle strain. It's an increase in energy when the tetrahedral bond angles deviate from 109.5. Deviation of tetrahedral bond angle. And that is 109.5 degrees. So we have lots of examples. Cyclopropane has an angle of 60 degrees. So it's a triangle. Cyclobutane is 90 degrees, so on and so forth. This is about 108, so it's pretty close. That's cyclopentane. Cycloheptane, etc. They've all deviated from 109.5. So all rings pucker means they adopt or conform to reach bond angles as close to 109.5 as possible. Only cyclohexane achieves 109.5. If planar, this would be 120 degrees, if planar. And it would have torsional, steric, and angle strain. But as it puckers, it only has minimal steric strain. So actually, in its puckered form, it doesn't have any angle or torsional strain. It's a very special puckered conformation called a chair. And use the thought of a chair loosely. Think of like a lounge chair or a chair by the pool or something like that. So these are the only ring conformers that you will have to draw, however. So you basically have to practice this, just like everything else. My suggestion is draw 100 chairs of each. There's two types of chairs. I'll draw those in a second. They're essentially three sets of parallel lines. Okay, notice the three sets of parallel lines, and every carbon has two hydrogens. Every carbon has 4 bonds, Each carbon is bound to 2 other carbons and 2 hydrogens. We call this a chair. And if we look down this bond, we see what are called Newman projections. We've gone over these. Seriously. It's carbon 1. The Newman projection shows you the steric strain. All angles are 109.5. All angles, all bond angles are 109.5. All dihedral angles are 60. Remember what this is, sort of a dihedral angle. And all groups are staggered. So I'm going to redraw the same chair down here. And this undergoes conformational equilibrium. I'm going to put in every hydrogen. That means it's out front. That's back in the back. This is 3-dimensionality. Okay? These are called axial. These are called equatorial. Notice that when this is called a ring flip, and it is not tumbling. We don't want any wedges or dashes. And the way to think about axial is it's on the axis up or down, and the equatorial is along the equator. It's kind of where the terms come from. When we flip this, I'm going to circle some of them. Okay, and make a circle. Put a circle on these carbons. The vertices, or the points here, are what's happening is we're flipping. And give you an example. This axial is the equatorial. When it undergoes a ring flip, all the equatorial hydrogens become axial hydrogens, and all the axial hydrogens become equatorial hydrogens. The same thing here. You can show that this is back by breaking the bond, sort of. And a couple things to notice. Again, all the axial H's become equatorial H's. All the equatorial H's become axial H's. So let's put a box around that one. Okay, axial, equatorial, equatorial, axial, equatorial, axial, equatorial, axial, axial, equatorial. Okay. So axial can be up or down. Equatorial can be up or down, but they're more out to the side. They're slightly up or down and pointing to the side. Notice that the equatorial hydrogens are parallel to sets of lines. So that equatorial hydrogen, I'm circling it right there. It's parallel to these lines. Okay, axial hydrogens are on the axis. They're up and down. Okay. So there's a lot going on here, as usual, and you need to draw 100 of each of these. These are conformers of one another. Draw 100 of them. One thing that this is not, it is not tumbling in space. It is called a ring flip, and that's really important. So we're going to ring flip. We're going to talk about conformations a lot. So let's show this ring flip. Let's draw the chairs again without all the hydrogens. It goes through a high energy intermediate called a boat. And then it goes through, let's show you the carbons that are flipping. This carbon's coming up, and now they're both pointed up. Now this carbon's going to come down, and they both kind of do this at the same time, but the idea is that it goes through this high energy intermediate called a boat. So we go from chair A to chair B. Same molecule, different conformations. It's conforming A to B. Okay. So I want you to redraw this, make models of it, build model kits, redraw it, put the hydrogens in there, practice. Okay, keep practicing. Again, notice that axial hydrogens become equatorial hydrogens, and the equatorial hydrogens become axial hydrogens. So you need to make models and you need to understand chairs. Okay? So that's cyclohexane. What I want you to sort of memorize, and there's a good reason for this. We're going to talk about it a little bit. We're going to talk about substituted cyclohexanes. So we're going to put substituents, methyls and ethyls and things like that, on the ring. And I want you to memorize that equatorial positions are less sterically hindered than axial. So memorize that fact, and we're going to go into a little bit of detail about why. So we're going to look at methyl cyclohexane. Back to the naming. We're going to look at methyl cyclohexane. So let's draw the skeletal version. There's an implied hydrogen of that carbon. We'll look at methyl cyclohexane. So we're going to draw both conformers. And you always draw all H's at a substituted carbon. So whenever I have a substituent, I want you to draw the H like I've drawn. So if the CH3 is in the equatorial in this conformation, the H is in the axial. And we're going to draw the other conformer. Keep circling these 2 points. Again, this is kind of coming up. This is coming down. So what has to happen, this CH3 is always down. If it's down in this representation and it's flipping, then it's got to be down here. And the H is up. H is up, H is up. H is axial, now H is equatorial on the right. CH3 is equatorial on the left, now CH3 is axial. So this over here on the left is the lower energy conformation. So we would show some equilibrium arrows like so. So a take-home practice, redraw same equilibrium with CH3 in the other 5 positions. Get used to drawing these rings. We're going to show some dye substituted here coming up. Now, before we get to the dye substituted, I want to explain why the equatorial is more stable than the axial. Let's redraw it a different way. Put the CH3 up first. We'll put all the H's in. Notice how the lines are drawn. There is a proper way to draw these. Every line that is equatorial should be parallel to two other lines. Okay. This is the least stable conformer, so we're going to flip. Again, look at this carbon in question. The CH3 was up. It is still up. It was axial. Now it's equatorial. Okay, so I've filled them all in for you again. Again, draw these 100 times with all the H's in there. Essentially, we call these 1,3 diaxial interactions. Okay. The methyl group is essentially interacting with the hydrogens, the other axial positions. Okay. And these 1,3 diaxials are actually gauche interactions. Okay. It's sort of just for your information. That's really what they are. If we were to look down this bond, for example, we would see gauche interactions. Okay. And but I want you to memorize that one of these 1,3 diaxial interactions, there's two of them here, A and B, let's call them. Each one is 0.9 kcals per mole. Okay, it's about a kcal. 1 kcal. That's an important number. I think just memorize it really for your information. But it's 1 kcal per mole, which is significant. Okay, so therefore, let's label these A and B. A is about 2 kcals per mole, technically 1.8, less stable than B, conformer B. Okay, that has implications. It comes out to be about 95 to 5, B to A. Okay, so let's show a few examples. Draw that one again. The methyl, just to kind of give you a picture. There's a steric interaction there. Again, this is methyl cyclohexane. There's about 5% of the axial. Okay, so 95% of it is in the equatorial, 5% is in the axial. Okay, there's 2 diaxial interactions. 1, 2. Same thing with ethyl. There's about 4% of this. This is called ethyl cyclohexane. About 4% of this conformer. There's about 96% of the equatorial conformer. Draw those. Okay, take home assignment, draw those. Let's draw the isopropyl. And this is helpful review for our substituents. Same idea, two diaxial interactions. This is isopropyl cyclohexane. There's about 4% of this conformer, 96% of the equatorial conformer. That's like at room temperature. Okay, so draw those three, and then I want to draw one more. This is the tert-butyl. Again, this nice review. To make the point, this is actually, you can see it's a lot bigger. The H here is small, and the isopropyl and the ethyl and methyl, but tert-butyl, that's no longer there. It's a lot of steric interactions. We just draw those lines to indicate steric interactions. So I'm not going to make you draw this and explain it, but you should know that the tert-butyl cyclohexane is about 0.025% axial. That means almost 100% equatorial. Again, draw that. Take-home message. So the take-home assignment is draw all four of these. Draw their conformational ring flip. And so that means they're going to, these groups are going to be in the equatorial. Take-home message is the tert-butyl always goes equatorial, meaning that a methyl, ethyl, or isopropyl on another part of the molecule in a dye-substituted system will prefer to be axial as opposed to a tert-butyl. Tert-butyl is never going to be axial when you have, if you have a choice. So we're going to see some dye-substituted cases. Okay, so that's where we're going next. We're going to dye-substituted. Okay. So, dye-substituted cyclohexanes. This is an intro to stereochemistry, which is chapter 6. I'm going to show you, we're going to look at some dimethyl cases. CH3s, two isomers are possible. I'll show you those. Okay, this is called the trans. The CH3s are on opposite faces. You see that? Opposite faces of the cyclohexane. The cyclohexane, even though it's a chair conformation, you can envision a plane running through it. The CH3s are on opposite faces, whereas the cis, use alliteration, cis is the same. They're on the same face. Cis. They're on the same face. So what you need to be able to do is translate this skeletal representation to a chair, and a chair to a skeletal. So you got to be able to go skeletal to chair, chair, chair to skeletal, back and forth. Okay, we're going to look at three cases. This is the 1,4 substitute. We're going to look at 1,4, 1,3, and 1,2. I'm going to draw it up there again, just very briefly. Here we haven't put wedges and dashes in there yet. Okay, so I'm going to show you the trans and the cis. I'm going to draw these the same way every time to help you learn them. So this is the trans we're talking about. And what I'm going to show you is I'm going to just keep the numbering 1, 4. So the 1,4 dimethyl cyclohexane, that's how you would name this. 1,4 dimethyl cyclohexane. And every time we're going to ring flip. So I'm going to start the rings the same way, and I'm going to flip them the same way so that you can get used to seeing I'm just arbitrarily numbering them right now, but 1, 4. Okay, now we have to decide which of these is more stable, lower in energy. Here we have, on the left side, we have 2 equatorial groups. On the right side, we have 2 axial. So the choice is clear here. The left conformer is more stable. Again, this is the trans. They're on opposite faces of the molecule. Okay. So take home, redraw the skeletal. One thing I want to stress here is that there's freedom in how you start. I'm going to kind of start the same way, meaning I've drawn it this way on the left. Once you draw it that way, you're locked in a sense, to where you go from there. And what I mean by that is we could have easily put the substituents, say, here and here. That would still be 1, 4. There's freedom in where we put them, okay? And then when we flip, there is those carbons need to be transposed properly. Okay, so the point is this carbon here, carbon 1, is this carbon, and this carbon here is that carbon. Okay? And you can look at the practice exam to see the types of questions that I would ask. Okay, I often give the skeletal and make you draw the chair. So yes, you must draw the chairs. Okay, and you must be able to take a skeletal and represent the proper substitution pattern, 1, 2, 1, 3, or 1, 4, and the proper cis and trans. Okay. So let's draw the cis now. Again, I'm going to draw the starting chair in the same way. I'm going to draw the ring flipped conformer. So now what do we have? This is the cis. Again, you should do the take home, draw the skeletal of the cis. These are completely equal. Why? Because we have 1 equatorial and 1 axial. 1 equatorial and 1 axial. They're equal in energy. So as opposed to resonance, where we said things are not going back and forth, these are equilibrium. They are going back and forth. They are conformers. They're not resonance forms. So they are discrete entities that go back and forth. So that's 1, 2. Oh, I'm sorry, 1, 4. Let's now do the 1, 3 case. So let me draw what I mean. These are at the 1 and 3 positions. I haven't shown wedges or dashes yet. Again, that's kind of your take-home assignment. Redraw the skeletal with wedges and dashes for all of these. So let's take a look. This is the trans. Now again, they are equal in energy. We have an axial and an equatorial and an axial. So they're completely equal in energy. Let's look at the cis, however. Here we have a clear favorite in energy, 2 equatorials versus 2 axials. So the one on the left is more favored, and this is the cis. Let's look at the 1, 2. That means this substitution, I've not put in the wedges and the dashes. We're going to talk about both, draw those out. and take a look. Here we have 2 equatorial. Here we have 2 axial. So again, the conformer on the left is more stable. This is the trans. Again, the methyl groups are on opposite faces. And I'll draw one of those for you. Now we're talking about the 1,2 substituted trans. Okay, they're on opposite faces of the ring. So let's draw the cis. Now you can see they're on the same face. Cis, both cis. And now we have equatorial, axial, equatorial, and axial. So these are equal in energy. You'll often find that with disubstituteds. You'll have one that's might be equal in energy, a cis or a trans, and the other one might be unequal in energy. So we'll take a look at these, and then we'll have a review session on Monday. Okay, and if we have time, we'll mention it tomorrow. I'm sorry, Thursday in class. And but you got to practice these. Make sure you practice drawing them. Put in all the hydrogens. Draw 100 chairs each. Understand axial and equatorial. Groups prefer the equatorial, and so when we start to look at disubstituted, you have to be able to identify the more favorable conformer and be able to go from skeletal to the most stable. For example, if I asked you the question, draw the chair conformation of the 1,2 trans dicyclohexane shown here. Draw that as a chair. That would be your answer. Both methyls are in the equatorial. Okay. So that's all I have.